Right, we need to do a bit of work on vectors, so it's sort of introduction really. So a vector is a quantity which has both magnitude and direction. So something like velocity is a vector, whereas speed just has magnitude. There's different ways of writing vectors. So the first one we're going to look at is magnitude direction form. So the way this works is we have a length r and an angle theta, and this is written as r theta. The length of the line represents the magnitude, and theta gives the direction. So we're basically going into two dimensions. So far all the work we've did in mechanics was just working on a line, but by introducing vectors we can start working in two dimensions. Right, this theta giving the direction is taken from the positive x-axis in an anti-clockwise direction, being positive. So people doing further maths really similar to complex numbers. So length of the line represents the magnitude, theta gives the direction, and this is taken from the positive x-axis with anti-clockwise direction being positive. So positive x-axis, that's the positive direction for the angle. So I'll give you a few examples. So e.g. 8 40 degrees, so you'd have a line of length 8, positive x-axis, that's 40 degrees, that's the positive direction. If instead we had 2 and 160 degrees, then the length of the line now is going to be 2, so it's going to be quite a bit shorter, and then this angle around here from the positive x-axis will be 160 degrees. And then one more, if I can squeeze it in, would be 5 and minus 60. So anti-clockwise is the, let's move it up a bit, anti-clockwise is the positive direction, so clockwise is negative direction. So this one is coming down 60 degrees, length 5, in a positive and a negative direction, which is a clockwise direction from the positive x-axis. This here is the same as 5 300 degrees. So you could go round in the anti-clockwise direction, which is the positive direction, 300 degrees, and end up in the same place as going 60 degrees in a clockwise, which is a negative direction. Right, the other form is component form. And this is where you go along x and up or down y. And then that creates your vector along the hypotenuse. This is written as xy, so you've probably seen vectors written as column vectors before. Or you can write this as xi plus yj, where I is a vector of magnitude 1 in the x direction, and j is a unit vector, so it's a vector of magnitude 1 in the y direction. So we're basically doing this. That's I, that's j, and they both have length 1. So if you go x in the I direction, x lots of I, y lots of j, that would be equivalent to doing this here. So it's just different ways of writing a vector. I tend to use column vectors more, but you should be able to use both. So e.g. 5, 2, we just go along 5, up 2, and there's the vector. If you had 3i minus 5j, then you go 3 lots of this unit vector in the positive x direction, and then you take away 5 lots of this unit vector in the y direction, and you end up with this vector here. So we've gone along 3, down 5. This is the same as 3 minus 5, so it's just different notation for the same thing. So hopefully that's straightforward. So something like minus 2, 4, we're going back 2 and up 4, and we've got this vector here. And that's the same as minus 2i plus 4j. Vectors are freestanding objects, so they can be moved around the xy plane, and then we fix an origin to fix points using vectors. We'll go on to that later on. Let's check the time on my video. I think we'll be right. So we can convert from magnitude direction form to component form. So we can go from one form to the other. So converting from magnitude direction form to component form. So for example, if we've got a vector 5, 60 degrees, so that I'll put it on an axis, it's length 5 at an angle of 60 degrees with a positive x-axis. And then if we wanted to write this in component form, that's x and that's y. If you're used to resolving forces, this is just going to seem really straightforward, but I'll run through it. So cos of 60 is adjacent over hypotenuse. And so x is equal to 5 cos 60, and you could just put that into a calculator, and that gives you 5 over 2. And then sine of 60 is equal to opposite over hypotenuse. And so y is equal to 5 sine of 60, which is equal to 5 root 3 over 2. We're kind of working in exact form a bit more now because we're not quite in applied maths territory at the moment. So in component form, this vector is 5 over 2, 5 root 3 over 2, or you could write that as 5 over 2i plus 5 root 3 over 2j. Vectors should always be underlined, that's why I'm underlining these little unit vectors. So they're the same. This works for any angle, so you don't need to overthink this. If you had a vector 4, 2, 2, 5 degrees, so this is coming around, all the way around, that's 180, 225, length 4. Then to convert that to component form, you can literally just do, same as I did here, 4 cos of the angle and 4 sine of the angle. So it works for any size angle, and that will give you minus 2 root 2 minus 2 root 2. We'll do a bit more work on trig in a month or so, but for converting from magnitude direction to component form, I don't know where to put this, I'll pop it up here, then r theta converts to r cos theta r sine theta. So that's my column vector. So it look a bit more like a vector, like so. Sorry, it doesn't look how I want it to look. Probably should have left it. So r cos theta, r sine theta. So it was really easy to see on this example. So r cos 60 gave us 5 over 2, and r sine of 60 gave us this y length, which is 5 root 3 over 2. And it will work with all these negatives as well. So you don't have to worry about it. You can just use this conversion. So to start with, if you could have a look at doing page 250, question 4 in your books, please. Thank you.